Welcome to the first part of our video series. In the next videos, you will learn the basics of Fusion, a CAD program used for computer-aided design. In Fusion, you work with components and assemblies. A component is a single object that cannot be disassembled further. An assembly consists of several components that can be joined together. In this course, we will model this air motor as an assembly. Its individual parts, such as the flywheel or the crank, are the components. At the end of the video series, the complete air motor will be animated and we'll see how it sets in motion. But before we begin with the construction, we must create a well-organized data structure. If you want to change the interface language in this tutorial, just click on your user at the top right, select Preferences, and change the language at the top to your desired option. If you have changed your language, you must restart the program for the change to take effect. First, we open the data panel by clicking it with the left mouse button. Here you can see the assembly as well as all associated components. Later, your air motor will also be found here that way. Now we create a new project. To do this, we go to the project list and click on New Project. We give the project a meaningful name. For example, Fusion Tutorials. This project serves as a folder where we store all components and assemblies. Thanks to Fusion's cloud-based working method, you can access your data anytime and from anywhere, as long as you have an internet connection. In our project, which we open with a double click, we first create a new folder. To do this, we click on New Folder, enter the name Pneumatic Motor, and confirm with the Enter key. With another double click, we open the folder. Here we will save all components and the assembly as separate files. The folder is currently still empty, but that will soon change. Now we start designing the base plate. This is cuboid shaped, rounded at the four short edges, and chamfered on the top surface. In addition, it has four symmetrically arranged threaded holes. You can also find the relevant component drawing linked below the video. To start, we click on File and then on New Construction. It is recommended to save the file right at the beginning. To do this, we click on the Save icon at the top left. The previously created folder is automatically suggested as the storage location. We assign a descriptive name such as base plate and confirm the entry with the Enter key. We see that the file has now been created in our folder. It can be seen that V1 is displayed to the right of the file name. This stands for the first version of the component. As the next step, we close the data panel to create more space in the workspace. In the construction process in Fusion, we start with a two-dimensional sketch, which we then transform into a three-dimensional body. Click on Create Sketch in the Solid Functions area. The program now prompts us to select a plane for the sketch. The three origin planes are displayed in the workspace. We will always draw the components of the pneumatic motor in the installation position, so we start our sketch on the XY plane. For this, we can simply click on it in the View area or select it in the Origin folder in the browser. As soon as the sketch is created, we see it both in the construction history at the bottom left, which lists all the tools used chronologically, and in the browser at the top left. This allows us to make changes easily later on. We are now in the sketch view. We can recognize this because we are in a different functional area, and the tools in the toolbar have changed accordingly. Let's start by drawing the base plate. To do this, we select Rectangle in the Create menu and then Center Rectangle. Moving the mouse pointer to the origin, a small blue square, which is called the snap, appears. The snap indicates that we can anchor the center of the rectangle precisely at the origin. Click with the left mouse button to start the rectangle and then move the mouse. A rectangle is displayed whose size changes as the mouse moves. We enter a width of 75 millimeters and a height of 45 millimeters. You can easily switch between input fields using the Tab key. Fusion works by default with millimeters, so we do not need to specify a unit. The unit is added automatically. Confirm the entry with the Enter key. Don't worry if you make a mistake. You can always use the undo and redo function or make changes directly to the sketch later. After the dimensions are entered, we click on Finish Sketch at the top. The functions for solid bodies reappear in our toolbar. Now we create a three-dimensional body from the sketch. For this, we use the Extrusion tool. Click on the rectangle and pull it up by 10 millimeters. Alternatively, you can enter the value directly in the distance field. Confirm the extrusion with the Enter key. The created body is now visible in the workspace. If you want to change the view of the component, you can use the View cube in the top right. With the Shift key and the middle mouse button, you can rotate the model. And with the scroll wheel, you can zoom in and out. If the part ever disappears, a double click on the middle mouse button is enough to bring the view back into the picture. The extrusion is now displayed in the construction history, where we can edit it directly with a double click. Additionally, a three-dimensional body was created, which we can find in the browser under the Bodies folder. Now we create a new sketch on the top surface of the part to add the holes. Right-click on the top surface and select Create Sketch. Alternatively, you can also select the Create Sketch function from the toolbar and then click on the top surface. If the body needs to be oriented differently for our sketch, we can simply perform a rotation of the body using the View cube. In the Sketch palette, we activate the construction line type and draw another center point on the deck. This time, we enter a width of 25 millimeters and a height of 40 millimeters. The construction lines are only used for alignment and are not visible in the final model. After completing the sketch, we also find it in the browser. In addition to the first sketch for the basic body, the second sketch for the holes has now been added. We can show and hide the sketches at any time by clicking the eye icon next to the respective sketches. All our previous steps are listed in the construction timeline. Here we see both sketches as well as the extrusion. To create the holes, we select the Hole tool and click on the four corners of the rectangle. The holes may now appear too large, as usually the settings of the last created hole are active. It might look different for you at this point. If you misclick, you can simply click again or use the undo command. Make sure to set the drill type to simple and activate the thread and thread offset. And set the thread size to M4. We set the drilling depth to 8 millimeters. And we set the thread depth to 6 millimeters. To represent the thread more realistically, we can activate the mode modeling. This ensures that the geometry of the thread is visible in the model. Since this makes the file somewhat larger and the calculations more complex, it should only be used in exceptional cases. Then we confirm the operation. To better recognize the drilling depth, we can switch the visual style in the display settings to shaded with hidden edges. Now the drilling is clearly visible through the component. Before we continue, we reset the visual style to shaded with visible edges only. We also edit the drill holes by double-clicking them in the design progression. Here, we deactivate the option Modeled Again. Next, we round off the model. We select the fillet tool and click on the 4 short edges of the body. If you clicked incorrectly, you can simply select or deselect the edges by clicking again. We set the radius to 10 millimeters. The rounding naturally also appears again in the construction history. To make adjustments, we could double-click the rounding element in the construction history. Now we use the chamfer tool to bevel the edges of the cover surface with a 1.5 millimeter chamfer. We confirm the process. The base plate is now completed. Note that the standard material is set to infusion on steel, which is the right choice for this component. We will take a closer look at how you can adjust the material in the material properties in the next videos. Open the data panel and save the file again. You can give the file a version description such as Final Design. The current version will then be changed from V1 to V2. Older versions can also be accessed at any time. Congratulations! You have successfully constructed the base plate of our compressed air motor and learned important functions of Autodesk Fusion. In conclusion, let's take a look at the entire construction process and summarize the essential work steps. Initially, you learned how to create a two-dimensional sketch and dimension it. Subsequently, the sketch was transformed into a three-dimensional body through extrusion. Then, you inserted threaded holes and adjusted the size of the threads. For the final touch, you refined the edges of the component by rounding and chamfering. These steps form the foundation for more complex constructions. But this is just the beginning. In the next video, we will design the cylinder head plate and get to know more exciting functions.